Table 310.16 of the National Electrical Code, or NEC, provides ampacity correction factors that can be used to adjust the allowable ampacity of conductors based on ambient temperature. Specifically, for ambient temperatures between 21 and 25 degrees Celsius, which is equivalent to 70 to 77 degrees Fahrenheit, correction factors of 1.5 for conductors with a use insulation rating and 1.4 for conductors with a THHN insulation rating are permitted. These correction factors are relevant in locations like Seattle, where the average temperature is approximately 24 degrees Celsius or 75 degrees Fahrenheit. The fundamental principle behind these correction factors is that higher ambient temperatures reduce the conductor's ability to dissipate heat efficiently. This, in turn, lowers the maximum current the conductor can safely carry without exceeding its insulation temperature rating and potentially causing damage or failure. Therefore, it's crucial to apply these correction factors to ensure conductors are appropriately sized for their intended application and operating environment. The process of using these correction factors is straightforward. Firstly, determine the uncorrected ampacity of the conductor. This is done by consulting Table 310.16 in the NEC. This table lists the allowable ampacities for various conductor sizes and insulation types, based on specific installation conditions such as the number of current-carrying conductors in a raceway or cable. For example, a 12 American wire gauge or AUG THHN copper conductor installed in a raceway with no more than 3 current-carrying conductors might have an initial ampacity of 30 amps according to Table 310.16. Secondly, identify the appropriate temperature correction factor. Based on the ambient temperature, select the corresponding correction factor from the table. In the case of Seattle, where the average ambient temperature is 24 degrees Celsius, the correction factor for THHN conductors is 1.4. Thirdly, apply the correction factor. Multiply the uncorrected ampacity obtained in the first step by the correction factor identified in the second step. This yields the adjusted, or corrected, ampacity of the conductor for the given ambient temperature. Continuing the example, the 12 AWG THHN conductor with an initial ampacity of 30 amps would have a corrected ampacity of 30 amps multiplied by 1.4, which equals 31.2 amps. This corrected ampacity represents the maximum current the conductor can safely carry at an ambient temperature of 24 degrees Celsius. It is crucial to understand the limitations and conditions under which these correction factors can be applied. Firstly, these correction factors are specifically designed for the temperature ranges and insulation types listed in Table 310.16. Applying them outside of these parameters may lead to inaccurate ampacity calculations and potentially unsafe installation. Secondly, these correction factors are additive with other directing factors. In situations where multiple directing factors apply, such as ambient temperature and the number of current-carrying conductors in a raceway, all applicable directing factors must be multiplied together to obtain the final adjusted ampacity. For instance, if there are 6 current-carrying conductors in the same raceway as the 12 AWG THHN conductor in the previous example, a further directing factor of 0.8 may need to be applied, according to Table 310.15. Final adjusted ampacity would then be 30 amps multiplied by 1.4 multiplied by 0.8, which equals 24.96 amps. Thirdly, these correction factors are intended for use in steady-state conditions. They may not be applicable in situations where the ambient temperature fluctuates rapidly or where the conductor is subjected to intermittent overloading. In such cases, more sophisticated ampacity calculation methods may be required. It is also crucial to consider the specific installation conditions when applying these correction factors. Table 310.16 provides ampacity ratings for various installation methods, such as conductors installed in raceways, cables, or freer. The correction factors must be applied to the appropriate ampacity rating based on the actual installation method used. It is essential to consult the NEC for detailed requirements and definitions related to ampacity, directing factors, and installation methods. The NEC is a comprehensive set of standards and guidelines for electrical installations, and it is imperative to adhere to its requirements to ensure safety and compliance. Ignoring these factors or misapplying them can lead to undersized conductors, which can overheat, damage insulation, and potentially cause fires. Conversely, oversized conductors can lead to unnecessary costs. In conclusion, using ampacity correction factors from NEC Table 310.16 is essential for ensuring the safe and reliable operation of electrical systems in environments with varying ambient temperatures. By carefully considering the ambient temperature, conductor insulation type, installation conditions, and other applicable dating factors, it is possible to accurately determine the allowable ampacity of conductors and select the appropriate conductor size for the intended application. Always refer to the latest edition of the NEC and consult with qualified electrical professionals for specific guidance on ampacity calculations and electrical installations.